Okay, in this video I'm going to walk you through the heat radiated power module. There is not a published paper on this yet. There probably will be eventually, but honestly I'm just so busy with Spark stuff I can't find the time. So these are some slides I created that's just sort of overview the algorithm, and so these will be basically what we're using until we get a real paper out there. So the objective today is to calculate the power that comes from a source object, so in here like a plasma, which is represented by this donut, onto a target. I guess I could go to full slideshow mode. And so if this is the vector between the two, we can create this sort of function, and there may be some errors in this math along the way, so I apologize if that's the case. But we're basically integrating over the source and calculating all these vectors, the flux vectors. So this is a radiance, and we're dotting it into the area of the target, J. So here it's S and T. It could also be I and J, and that's sort of what this is using. So if you do that, you end up getting the power here ends up with this dot product sort of thing that is basically the dot product of this R vector into the normal vector. Scale it by the area. So this is sort of the incident angle, this is the area, and then this is just the regular like power fall off for a point source. So we can do that, and then we can do a bunch of different point sources. And so then we just integrate over all of the source and all of the target points. This is the power going to target element J. So this is that mesh element. And so we can see that it's this integral over the area of J times the integral over all of the sources to all of the targets. And the reason you need that is because we're doing this delta function, which is just a mapping that says this there's this vector R, and there could be another CAD object here that is blocking it. So if there's a CAD object, then this is going to be a shadow. So this function is basically just the shadow mask calculation. So this is shadow mask if you're familiar with heat. So we're doing the cubed and then the shadow mask. So if we can make it from here to here, then this would be 1, and then you can weight it by the flux or the irradiance. So this is how we do it, and then you can actually do that all over the entire mesh. And so you're now integrating over all of the potential TJs. And so this is sort of the philosophy here, is we're treating all of the plasma as a discrete number of source objects, point sources. And in the limit, as you increase the number of point sources and the number of targets, you'll approach the true continuous functions. So in heat, what we do is we're going to take this slice, and that's going to, if we look at a cross section of that, there's an R and a Z coordinate, and we'll break it into cells, right? So each one of these sources will have like here I'm just putting them at the center of each cell, and then we can calculate the area for each source. So for like source I, we have dr and dz I, and that's AI, and then we can take the volume is approximately the 2 pi r times that source if these are small, and then you can take the power density and multiply it by the volume, and that's how you get pi. So that's what pi is. Each one of these source points is in units of watts or megawatts. In heat, they're all megawatts. So, and they represent the toroidally integrated power density function. So if we had the emissivity profile in megawatts per meter cubed, you would integrate it toroidally on its grid, toroidally and radially and in the Z. So you'd integrate it in all 3 dimensions, and that's how you get out this P. So if you come with an emissivity profile, you need to build an interface that gets you P, basically. And I'll talk about some of the interfaces I have as examples in a second. So then we're going to weight this. So what we're going to do is, like, let's say that we only care about this region, like the tile that we're trying to calculate the heat flux on is right here. We probably don't need to do all of the tokamak. Like, if you wanted to be completely theoretically correct, yeah, you would. But you can get away with doing just really like the the section of the toroid that's just around that PFC, because the contributions from way over here are going to be very small to the flux on a tile here. So what we'll do is we'll set a minimum toroidal angle and a maximum toroidal angle, and then that'll give us our delta phi here, and that's over 2 pi. So we'll weight that power, which is, you know, volume times power density. We'll weight that power by the fractional component of the toroid, so that's this, times the number of discrete samples that we're taking through there. So what we're going to do is we're going to take this RZ profile and just sort of pattern it through this angle from phi min to phi max n tor times. So here it's showing 3, n tor equals 3. You could do 20, you could do 100. As you increase the number, your computational cost is going to go up. But the idea is that there's a solution that's good enough with a low number of n tor. And for, you know, a few degrees, I've been finding you can usually get away with 10 to 20 n tor. And, you know, it's pretty fast on a single CPU. So this is sort of how we weight that power compared to the entire integrated power. We cut it up into a toroidal slice, and then we basically say, like, each one of those slices within that chunk of toroidal angle is going to have a weighted power contribution. And so, like, here's an example of a single RZ grid where I've, like, put this torus in it, and so it's the power is decaying because it's uniform power density in this, and so we're increasing in radius, right? So that's this x coordinate. So as we're increasing in radius, we're falling off our toroidally integrated power. Or actually, sorry, I just misspoke. We're going up in our toroidally integrated power. So that's why you increase, not fall off. Everything I just said, just flip it. It's a function of the volume, right? So and we have that 2 pi r term in the volume, so that's why it's going up. So, but the power density is uniform over this, is the point. This is a single slice. And then if we take that and we pattern it, like I mentioned, so here's an example of 9 slices. We take that same pattern and we pattern it. You can see the peak megawatt goes down. And that's because we're dividing that same region from phi min to phi max now into 9 different components instead of a single one. And so this is a factor of 9 difference. So that inverse n tor. So this is sort of the idea, is we're going to take an axisymmetric power profile, revolve it in 3D, and then do photon tracing from every one of these points down to the target. So here's some examples. Like if you just put one inside this box and you put it sort of close to this edge, you'll see that there's a lot of power right there. There's a little bit there. There's a little bit there. And then if you do the full 9, you start distributing that power profile over the entire box. So here's a 45-degree slice of the toroidal angle, and n tor equals 9. And then, okay, so here I'm just talking about how we're doing energy balance in heat. So this required a little bit of creativity. So what we're going to do is we're going to take this point, for every point, like let's say that it's the middle of a unit sphere. So I'm just taking an example point out of this RZ coordinates, put it in the middle of the sphere. Okay, here's the sphere. And then here's some mesh object that I'm trying to calculate the power on, okay, or the heat flux on. So this could be like your diverter tile or whatever. Here's one of those source points. We're going to do this for every single source point. We're going to construct this vector between each mesh triangle center and the source. And then we're creating this normalized sphere around it, that vector. So we normalize that vector and create this unit sphere, and then we figure out where do all of the coordinates intersect the sphere. And so that's what you're seeing here. If we plot in like this sort of spherical coordinate, we can see the distribution of all of the mesh centers as viewed by the sphere. We can then construct, and there's some math down here if you want. We can construct this convex hull, which is basically what is the shape that bounds all of the points, right? And so then calculate the area of that hull, And if we divide area over 4 pi, we should be getting the fractional component of the power that will land on the mesh. And you can see if we add up all the radiated power to the PFC, so this is like adding up all of those mesh element megawatt per meter squared times the areas that land on this PFC, this cube for that example where we have the power source in the middle, and then we compute the convex hull radiated power. So we're basically taking how much of this power for each point. We trace all the mesh triangles down to the unit sphere and then calculate the boundary of it, and then we see what's the difference. It's within a % here. So this is how we do power balance for the radiated power calculation in heat. Some caveats are, if you are running a power profile, like if I had this, if I had a PFC like right here, so very close to the RZ points, it'll start to get worse. I've seen it go up to like 50, 60, 70, 80%, but it won't be like several thousand %. So as you get closer, it's just the discretized nature of this convex hull will have a bigger impact. So it's a tool, this convex hull calculation to use, but it's not really something you should completely trust, but it is something that will give you a good indication of if you are in the ballpark. Okay, so now that I've shown that, I'm going to show some examples. So this is what the power profile that heat likes to eat looks like. So we have R, Z, and then power. It's like this is an example profile that would generate some kind of a point cloud like this. So this is an RZ axisymmetric power profile, and we can see that like there's a lot of zeros, and then there's this sort of toroid in the middle, which we're going to revolve. You know, you can revolve this if I do that and then rescale it. Like here's 5 times. You can revolve it as many times you want in order to get the loading on the PFC that you want. So if we go back to here, so basically there's some tools to make these in heat. So there's a repo in heat called, if I can find the, it's plasma potential heat tools. And there's a bunch of tools in here, GQS tools, mesh tools, open foam tools. So we're going to go to rad power tools and look at this create 2D rad file. So in this file, I'm going to actually open it in Atom, create 2D rad file. So in this file, you're going to define where you want to save your CSV file. You're going to define the min and max boundaries of the grid. So that would be like Rmin, Rmax, Zmin, Zmax. And then the number of points in each direction, the number of cells. You're going to define a minor radius here. So this is like saying I want a torus of 20 millimeters in width. You're going to find the total power. So this is that integrated power around the entire tokamak. So if you did like this integral here, this pi, if you integrated this over the entire RZ plane, you would end up with this power. Oops, this power. This manual center. So like this could be thought of as the entire toroidally radiated source, right? So if I have a torus that goes all the way around the machine, this is all the power that comes out of it. Then manual center basically allows you to define the center, the R and Z coordinate of the center. This won't line up with our example today, these coordinates, but R center, Z center would be if I wanted to define like the dead center of this, and then it'll be 20 millimeters, that minor radius is how I define this toroid object. So once I have all those, I basically just, I change those inputs and I run the code and it will spit out, it does all of this weighting, it calculates the volume, and then it spits out this RZ power file for you. So this is just an example. You don't have to use this. This will be a uniform power density, non-uniform power like I showed earlier in the slides. But this is just an example of how you would create these. It doesn't matter what your input is as long as it is, your input workflow is, as long as it comes out in this form. Heat can read it. So another example I was going to show is this SolPS stuff. So you can basically take a SolPS class. There's a SolPS class in that file here, and you can, using this read SolPS output script, you can read that. So like here I'm reading the neutral, the line radiation data, the neutral radiation data, and then like the temperature data. And then here's the geometry, the B2F geometry, and then here's just a CSV for the RZ contour for the machine. You can select where you want to save out this file again. So that's the name of the file that we want to save. And then this box is, if we don't want the entire SolPS RZ output, because that's the entire tokamak, we could just select like a region of the diverter where you want a box. And so then I create that CSV file, and then there's some plots at the bottom here. Yeah, so I'm gonna show a slide or two from my APS talk this year for Spark. So here's an example of a SolPS output. You can use the SolPS IO class and that workflow I just showed you to generate the point cloud, the RZ point cloud. You can then revolve it toroidally and then do the photon tracing. So this workflow here is how you would do that. So I think that sort of covers some of the ways to do inputs to heat for the radiated power profile. Basically, all you need is this file, right? This RZ power file. So once you have that, then you can go into the heat GUI, which, where did I leave that guy? So I've already run these cases, so I'm not going to run them again, but you're going to come to this photon heat flux setting and do your minimum and maximum phi. Remember, that is this, where is it? Minimum and maximum phi are the angles within which you're going to put all these discrete axisymmetric profiles. And then the number of toroidal repetitions is just an ntor in this slide. Okay, so this is the bounds, phi min, phi max. This is the number of toroidal repetitions. Excuse me. So it's pretty easy. You just put those in. You just take this rad file. Oops, that's the videos. Let me open that. I think so. In the test case, I've included one. So you can just take that, drag it, and drop it in there. It'll load, set up this, load all that, those rad settings, and then you just come over here, do photon radiation heat flux point cloud, and then you run it, and then you run heat. So for this example that I just did, I accidentally did 2 PFCs in this one, which I should have only done 1. So it should be about half this time. But you can see it was pretty quick for the second PFC was, it looks like, what is that, 15 million or is that 5? Yeah, 15 million. And then the first one was, and you can see here's the error between the convex halls, 1%. And then, so this is solid 843. This is the one that we cared about. The error for that one was 1%. And that took, so this one was 45 million ray triangle intersections. And this one was 15 million. So that's 60 million ray triangle intersections. Yeah, so pretty quick. This one had a 0.25 convex hull error. So the power balance is pretty good on this. And then we can look at sort of the outputs. So if we just are looking at this single, I'm going to turn off this object. The single slice, it'll be a little weird looking. So you can see that it's, as we would expect, the flux on this PFC is highest right under where we've put that slice, right? Because this is a ntor equals 1 run of heat, right? So it still creates a profile, but it's, it's not really realistic. Excuse me, because you have this super steep gradient going in the toroidal direction. And then if we look at our 5 different slices and we look at the profile for that, so let me turn off that one, it's much more uniform. It'll still be a little bit discrete. You can see that it's sort of favoring over here. It's a little bit whiter than it is over here, and that's because this doesn't cover this PFC fully. See that? So in the limit, as you increase your width of your toroidal angle and you increase the number of toroidal slices that we're using here, this profile will converge to the real heat flux profile. So it's up to the user to sort of go through and figure that out. But yeah, so that's basically how you run it. And these files are all in the Solid 843 pair view folder. So you have the rad, the PRAD, that is the point cloud for the power. That's the axisymmetric profile. And then the heat flux rad is the actual flux onto Solid 843. So you can see both of them, they both come out of heat. So that is an overview of the radiated power calculator. You know, eventually we'll get to doing reflections and stuff, but honestly, it doesn't really, the reflections are not going to melt wires or bolt heads or something. It's the first, from the donut to the tile that is going to melt stuff. So that's what we're concerned with in heat, and there are other tools to do that, like Cherub or Raysect. So this is, the goal of this is a highly deterministic, fast calculation. And like I showed for this APS slide here, 750 million photon traces can be done in like an hour or two. So it's about 1 billion traces an hour, and this was on a desktop. So I think that this is a pretty powerful tool, and it should add and augment the already existing capabilities in heat. If you have any questions, please submit them to the heat GitHub issues tab, and I will try to answer them in a timely fashion. So thanks for watching. Good luck.